All right, hopefully folks can hear me. I think we'll go ahead and get started today. Welcome to our next Landscapes Live seminar, the online geomorphology seminar series. Thank you all for coming week after week. We have one more talk after this week in our spring session. That's next Thursday at the same time, and that'll be by Georgie Bennett. And then after that, we'll be taking a break for the summer and coming back in the fall with more great talks. And today we will be hearing from Fiona Clubb. I will be chairing the session, and then we'll have sort of questions and facilitation by Steffi Tofelde and Pierre Vallat. Fiona will be talking about creepy landscapes along the San Andreas Fault, and she's coming to us virtually from Durham University, where she's an assistant professor. Before that, she was a postdoc, a GeoX postdoctoral fellow at Uni Potsdam, and before that did her PhD and undergraduate work at the University of Edinburgh. So thank you to everyone for joining us, and we will transition over to Fiona's slides now.
Okay, great. Thanks, Charlie. Let me just share my screen.
Oh, sorry. One more thing. Questions. You can ask questions in the chat. We'll open the chat up for questions towards the end of the talk. And then our facilitators will typically read the questions, and we'll get those answered.
Okay, great. Well, thanks very much, Charlie. Just to check, can everyone hear me okay?
Yes.
Great. So I'd like to start by just thanking the organizers for inviting me to give this talk and for all their hard work in setting up this seminar series. I know everyone have really appreciated it while I've been stuck at home, so thank you. So today I'm going to be talking to you about tectonic geomorphology, and specifically talking about landscape morphology along the San Andreas Fault. So I've titled this talk Creepy Landscapes, and I'll come back to that later in the talk. So this work is done in collaboration with several co-authors listed here, so I'd just like to start by thanking Simon, Martin, Stuart, and Bodo, without whom none of this work would have been possible, so thank you all. So in this talk, I'm going to be focusing on how we can firstly quantify the shape of Earth's topography, and secondly, how we can link this to tectonics. So as geomorphologists, many of us are interested in the interactions between processes that erode and transport sediment on the surface of the Earth with climate and tectonics. And we might see Earth's topography as being the kind of boundary between these different processes. And therefore we could infer that the shape of this topography might give us insight into the interactions between these processes. So in this talk, firstly, I'm going to give a brief overview of how we can detect tectonic signatures from topography. And then I'm going to give you two examples of where we've applied this. Firstly, I'm going to talk to you about a broad scale analysis of the San Andreas fault system, looking at continental scale fault dynamics. And then secondly, to provide some more detail on the links between tectonics and topography at the Mendocino triple junction, which many of you might be familiar with. So why might it be important to investigate the surface expression of tectonics? Well, if topography reflects tectonic processes, it means that we might be able to use the shape of topography on its own in order to investigate and better constrain the subsurface. So I'm showing here two examples recently where this has been done. So on the left is some work from Vincent Godard and colleagues that was published in eSurf earlier this year, where they used the morphology of channels and hill slopes along this ridge system at the site in southern France to detect the signature of a blind thrust structure in the subsurface. We can also look at this on a larger scale. So on the right, I'm showing some work of Catherine Groves, who's a PhD student at Durham, who was looking at the distribution of elevations across the Quilian Shan and showed that this distribution of elevations corresponded between the transition between lock to creeping sections of thrust faults. This can be really important for seismic hazard assessment, for example, as we know that there are different seismic hazards between locked and creeping sections of faults. So in many places throughout the world, topographic data are really the only data that we have available. This is particularly the case in kind of developing regions or understudied areas of the world. And this therefore really gives us the opportunity to do things like identify blind thrusts and improve seismic hazard assessment from topographic data alone. And this is a really exciting time, I think, to be working on this problem, because the availability of high resolution topographic data has increased exponentially in the past few decades. So I'm just going to show you an example of this. I stole these slides from Simon to show just how the resolution of topographic data has changed over the past 30 years. So what you're looking at here is a section of the San Andreas fault this is a hillshade from the 90-meter SRTM dataset that was collected in 2000 and released in 2005. And you can see here, this is the strike of the San Andreas fault. This is at the Dragon's Back Ridge. And you can see from these data that it's really difficult to pick out fine-scale geomorphic structures along the fault. If we compare that to the data that we have available now, so this is a LiDAR hillshade from the same region, you can see that we can now pick out fine-scale channel and hillslope features along the strike of the fault. And this means that we can now look at the influence of tectonic processes on the landscape at much higher resolutions and finer detail than previously possible. So how can we detect the signatures of tectonics from topography? Well, one of the most influential papers on the subject was published by Wobus and colleagues in 2006. And it's nicely titled Procedures, Promise, and Pitfalls. And in this paper, they set out some nice guidelines on how we might do this. And their work and much work subsequently has kind of focused on river profiles. How can we use the morphology of river profiles to tell us something about tectonics? And the standard way of doing this, I'm sure many of you are familiar with, but I'm just going to give a brief overview to make sure we're all on the same page. And it's channel steepness analysis. So what we would do in this approach is for a river, we would plot on the x-axis here, the drainage area at each point along the channel, against the channel slope on the y-axis. We normally do this in log-log space. And empirical studies of many rivers throughout the world have shown that if you do this plot, you get this nice inverse relationship between slope and drainage area that can be described by a power law. So just to point out, the data I'm showing you here is for a landscape evolution model, which is why it looks so nice. But what we can do is we can regress these data to fit this power law, and that allows us to get Ks here, which is the channel steepness. And we can think of this as being the kind of overall steepness of this stretch of channel normalized for the drainage area. And what we would do then, if we want to compare the steepness of channels across an area, is we would normalize this channel steepness for a reference channel concavity. And that would allow us to get the normalized channel steepness index, which we call here KSN. And KSN is really the standard topographic metric that's being used to link river profile morphology with tectonics and with climate. And this metric has been really, really useful, and it's been shown to correlate very well with uplift rate, for example, across a number of different settings. So what I'm showing you here is some analysis from Kirby et al. In 2007 along the Bolinas Ridge, which is just to the north of San Francisco. And what they did is they analyzed the steepness of these channels which drain along the fault, shown here. And they found that the steepest channels correlated with the inferred area of highest uplift along the fault. So this channel steepness can be a really powerful tool that we can use. However, despite this, there are some problems with channel steepness data, which I think it's useful to consider. The first of these is that if we make these plots of slope against drainage area, we can have significant gaps within the data, such as here, which is just a result of the inherent branching nature of river networks. You're always going to have jumps in drainage area at tributary junctions. We can also have order of magnitude different slope values at a single drainage area. So this here is a typical slope area plot from a river in China that we just took from the SRTM. And you can see that at this drainage area, for example, we have a very wide range of slope values. This can either be due to noise within the DEM, or it can be due to geomorphic noise. So things like the presence of alluviation within channels, for example. And you can imagine that the presence of this noise makes it very difficult to fit a power law through these data to get an appropriate channel steepness. The second problem with this channel steepness approach is that landscapes are inherently heterogeneous. So in order to illustrate that, I'm showing you here the results from a landscape evolution model. It's a really simple model where we just run fluvial incision. You can see we've just got a rectangular domain. And we just set some random boxes which have different rock types. So they're kind of shown by these square patches here. And they represent areas of softer lithology. And I'm going to show you the slope area plot from Basin 2 here, which you can see drains both this harder lithology to the north and the softer lithology. So that's what the slope area plot would look like for this basin. And you can see that this lithological contrast results in significant noise or different regime within this slope area plot, which would make it very challenging to extract a kind of overall steepness for this basin. And so following on from this, some work has looked at how can we go beyond river profiles and try and look at the signatures of tectonics and perhaps climate in the rest of the landscape. So this would be analyzing metrics associated with the hill slopes and the hilltops, as well as with the channels. And I'm going to be talking about some of these metrics in the later part of my talk. So some of the things that we could look at would be things like the steepness of ridges in the landscape. So you can see here, the hilltops are picked out here in red, and we could look at how steep these hilltops are. So you might intuitively expect that if you have a very steep, rapidly eroding landscape, you might have steep, narrow ridges. So think of the Alps, for example. Whereas if you have a kind of smooth, diffusive landscape, say the Appalachians, you might have much kind of more smooth, wider hilltops. So that's something that we can look for and quantify in the topography. Other things that we can look for are the length of hill slopes. So we can route flow from these hilltops down to the nearest channel, and we can measure the length of each of those flow paths. We can then use this to get the hill slope relief, so the difference in elevation between the hilltop and the nearest channel. So I'm going to show you some kind of two examples of how we can use a variety of different techniques to detect the tectonic signatures from topography. And I'm firstly going to give you a broad scale analysis from the entire San Andreas fault system. And then I'm going to zoom in and talk to you about the Mendocino triple junction, which is a really interesting kind of field site in more detail. Okay, so firstly, let's think about this kind of broad scale analysis of the San Andreas fault. So hopefully everyone is kind of familiar with the San Andreas fault system. It's a right lateral strike slip fault, and it's one of the best studied and monitored fault systems in the world. I'm going to start by just giving an overview of the tectonic motions along the San Andreas fault that we can see from modern day observations. So we can broadly split the San Andreas Fault into 3 different regions, which hopefully I can show here. So we have 2 locked sections of the fault, one here to the north and one here to the south, where we can think of the plates as being kind of stuck together and not freely slipping past each other. These tend to have large historical earthquakes, such as the 1906 San Francisco earthquake, which devastated much of the city center. In between these 2 locked sections, we have the creeping segment of the San Andreas Fault, which I'm showing here in red. And in this section, we haven't had any large historical earthquakes. And if we look at the GPS and INSAR data along the fault, we can see that there's a big change in slip rates here. So this graph here I've taken from Tong et al. In 2013. And what they've done is they've plotted the latitude on the x-axis. So we're going from north on the left to south on the right. And the y-axis is the right lateral slip rate. And we can see this creeping section of the San Andreas Fault picked out by this big increase in right lateral slip rate, where slip rates go up to around 30 millimeters per year here. So one of the questions we wanted to ask is, can we see this representation of this fault behavior in the topography of the region? Just to point out here that we can also see this creeping section of the fault if we look at the historical earthquake record for the San Andreas. So what I'm showing you here is all of the earthquake data from California. So this is every earthquake of a magnitude greater than 3 from 1900 to 2020, not counting the past few days because I made this figure a few days ago. And what we can see is that the creeping segment is quite well picked out here. So in this region, we have quite frequent earthquakes, but they tend to be relatively low magnitude and at kind of medium depths. So we wanted to look at the effect of fault dynamics on the topography here. And we're really lucky for the San Andreas Fault in that there are LiDAR data available for the entire strike of the fault. So this is around 1,200 kilometers. These are all available on Open Topography, so you can go and download them. So what we did is we downloaded all of the point clouds and we reclassified these to create a 1 meter DEM for the entire fault. So this was around 18 billion points, so this took quite a long time. But yeah, we have around 4 terabytes of DEM data that we've analyzed. So in order to kind of look at topographic metrics, for here I'm going to be firstly focusing on river profiles. So what we did was we extracted every 3rd order drainage basin along the strike of the fault. So an example is shown here, where you have the kind of drainage basins shown in white. And then we extracted the longest river channel in each of these basins and calculated the gradient of the channel in each of these basins. So for this broad scale analysis, we decided not to take the channel steepness approach. Because of the large scale of the analysis, we didn't feel confident in assuming a reference concavity for the entire fault. So we've decided to go for this more kind of just topographic based approach of channel gradient. So the longest channel in each basin here you can see colored by the gradient. What we then did is we separated these channels into the 2 different plates on either side of the fault. So we have the North American plate to the east of the fault strike and the Pacific plate to the west of the fault strike. So that's what I've done in these plots here, and you'll be seeing a few of these plots, so I'll just explain them now. So on the x-axis, we have distance along the fault going from the northwest to the southeast. And on the y-axis, we have the channel gradient, where we have the North American plates in red and the Pacific plate in blue. And what we did is we took each of those river basins and we binned them into kind of 1 kilometer spacings along the fault. And we took the median channel gradient in each of those 1 kilometer bins. And that's shown by these kind of gray points here behind these data. We then fitted a 10-point rolling median through these bins, which is what's shown by the red and the blue dashed lines. So when we did this, the first thing that kind of jumped out at us was that we have significant peaks in channel gradient along the strike of the fault. We therefore ran a peak finding algorithm to find these local maxima, which are shown by these black stars here. So I'd like to just go through each of these peaks and have a look at where these peaks are occurring in relation to the fault dynamics along strike. So the first peak that we found was around 370 kilometers along the fault in the Santa Cruz Mountains. And you can see that we found this peak in both the North American plate rivers and the Pacific plate rivers. The location of this peak is shown on this map by the red star. And we can see that this peak corresponds to the transition point between the locked section of the fault to the north and the creeping section of the fault to the south. We see the same story if we look at the other transition point of the creeping segment with the locked segment to the south, where we can again see a significant peak in the channel gradients at this point. If we go further south, we get these very low channel gradients that we start to see. And if we compare that to the GPS and INSAR measurements along the fault, that's what I'm showing here on this bottom panel. We again have distance along the fault. And here's right lateral slip rate. We can see that these two peaks in the channel gradient tend to bound either side of this creeping segment where we have much higher slip rates along the fault. So this is suggesting here that this transition from creeping to locked fault behavior is affecting the gradient of channels in this region. And some modeling work has shown that if you have creeping to locked transition points of faults, you can get very focused uplift at either end of the transition. So this is reflected well within our data. The third peak in our data that we see in channel gradients is located around 730 kilometers along the fault in the San Gabriel Mountains. And if we look at where this is occurring, this correlates to the start of the Big Bend, where the direction of the fault strike becomes oblique to the direction of relative plate motion. We then see our final peak in the data, which occurs here on the Pacific plate at the other end of the Big Bend, where again we have to the south of here, the fault strike again becoming parallel to the direction of overall plate motion. Some of you may be wondering why we don't see this same peak in the rivers on the North American plate. And this is simply because there's a discrepancy between our mapped fault strike here and the flight path of the LiDAR. So all of the LiDAR here is located on where we would say the Pacific plate is. So in order to investigate this further, we decided to do an analysis of the azimuth of the fault strike as we go from north to south. So to do this, what we did was we took the strike of the fault, which is shown here by this black line, and we again had a point in 1 kilometer intervals along the strike. So at each point, what we do is we calculate the azimuth between that point and the next one, which is shown by this kind of angle here. And we then calculate the difference between this calculated azimuth and the overall direction of plate motion, which we've set here to be 135 degrees. So that would be just a kind of line going northwest to southeast. So that allows us to calculate this metric delta azimuth. And if delta azimuth is positive, this means that the fault strike is more southerly facing than the direction of overall plate motion. And this would mean that the fault is going through a releasing bend. If delta azimuth is negative, on the other hand, this means that the fault strike is more easterly than the overall plate motion. And this would be a restraining bend, where we would predict there to be uplift. So that's what I'm plotting here in this bottom figure, where the y-axis here is this delta azimuth. And if you're in the blue part of the the plot, then it's a releasing bend. And if you're in the red part of the plot, it's a restraining bend. And what we can see from this geometry analysis is that the location of sharp restraining bends on the fault very well correlates with these peaks in channel gradient that we see to the south of the San Andreas Fault. So this is suggesting that fault geometry has a really strong control on topography along the system. So I'm sure many of you are thinking, well, hold on, we know that there are many other factors that can influence channel gradient alongside tectonics. And one of these could be lithology, for example. So we've tried to address this, and admittedly, this is a very hard thing to do over such a broad scale. But we've taken the geological map of California and we've split it into 4 main groups. So we have alluvium, sedimentary rocks, metamorphic, and igneous. And we can then look at the distribution of channel gradient in each of our rivers, separated into each lithological group. So that's what I'm showing here. We have the same plots as before, where we have distance along the fault against channel gradient on our y-axis. But this time, the channel gradient data is separated by lithology. So the yellow curve represents sedimentary rocks, for example. And when we do this, we find that these strong peaks in the channel gradient, such as here in the Santa Cruz Mountains, are consistent across multiple lithologies. So for example, in the Santa Cruz Mountains, we see a peak in channel gradient in both sedimentary and metamorphic rocks. And in the San Gabriel Mountains, we see it in both sedimentary and igneous rocks. And this suggests that over these broad scales, at least, lithology is not the dominant control on channel gradients. So I'm sure that lithology has a big control on channel gradient, and it's probably the cause of a lot of noise within our data, but I think over this scale, we can make the case that it's not the dominant control. So what implications can we draw for fault dynamics in the region? Well, we kind of showed that the peaks in channel slope that we see along strike seem to correlate well with the transition points between locked sections of the fault to creeping segments. And this also correlates with the location of frequent low magnitude, medium depth earthquakes along the San Andreas Fault. We found that fault geometry is also a really important control on channel gradients, especially through the Big Bend in the south of California. And I would perhaps argue that the fact that these channel geometries are well reflected by modern fault dynamics that we can measure from modern observations such as GPS and INSAR suggests that this creeping section of the fault must be a relatively long-lived feature in order for the channel gradients to reflect these modern observations. So now I'd like to take you to a second case study of the signatures of tectonics from topography. And I'd like to stay with the San Andreas Fault, but I'm going to zoom in on one particular section and show you in a bit more detail and kind of go beyond river profiles to look at the influence of tectonics on hill slopes and hilltops. So I'm going to focus on the Mendocino triple junction, which is located at the very northern end of the San Andreas Fault, located here by this red star. And the Mendocino triple junction marks the meeting point of 3 tectonic plates, so the Pacific plate, the North American plate, and the Juan de Fuca plate. And it's a field site that's been really used a lot in geomorphic studies. And the reason for that is that it's a really excellent place for exploring the links between tectonics and topography, as we have very good constraints on uplift rates along the coast. So there are these beautiful marine terraces preserved along the coast, and these were dated by Meritz and Bull in 1989, and they allow us to explore how uplift rate changes as we go south along the coast. So here I'm showing some work by Snyder et al. In 2000, where they analyzed these small river basins, you can see here, draining along the Mendocino coast, and looked at how the morphology of the rivers changed with the uplift rate. What we can see if we look at how the uplift rates vary as we go from north to south along the Mendocino coast is that there is an order of magnitude variation in uplift rates as we go from north to south. And geodetic work has shown that this uplift rate gradient is caused by the northward migration of the triple junction through time. So it's going from south to north, I think around 5 centimeters a year. And this means that we can break the rivers kind of into 3 different zones based on what their uplift rate is. So the basins in the south here, we can say are in a low uplift zone. So these basins used to be uplifting more rapidly when the triple junction was more to the south. But as the uplift wave migrates northwards, they're now experiencing lower uplift rates of around 0.5 millimeter a year. If we move a bit more north, we go into the King Range, and here the rivers are currently experiencing a high uplift. So this is the high uplift zone, and uplift rates here are around 4 millimeters a year. Then just to the north of the range, we have what we can call the transition zone. So these basins are only just transitioning into the zone of high uplift, and they have kind of intermediate rates of around 3 millimeters a year. So you can kind of imagine that through time, as the triple junction migrates to the north, the location of these different zones is going to slowly shift to the north through time. So we wanted to explore in more detail the impact that this uplift wave has on the topography. And what we did then was we took 25 basins which are draining along the coast. So I've kind of flipped the hillshade around here. So north is to the left of the slide. And these are similar basins to those analyzed by Snyder et al. And we basically analyzed a bunch of different topographic metrics within these basins to see what signatures of tectonics we could find in the landscape. So firstly, let's think about the channel network. So we performed normalized channel steepness analysis on each of the river basins. So this work has already been done by previous authors, but we wanted to look at the distribution of channel steepness within each basin, as well as just having one overall number for each basin. And we also looked at the drainage density, or the degree of dissection of each basin. So you can imagine that if you have a channel network that has a low drainage density, it might look something like this, so it has very few tributaries. Whereas if you have a high drainage density basin, it will have lots of tributaries. So it's got more channel length per drainage area. So we analyzed each of those metrics for the basins along this uplift wave gradient. So what I'm showing you here in the bottom panel is again this uplift rate pattern. So we have the basin ID on the x-axis of all of these plots, where we have north on the left and south on the right. And we can see I've plotted each of these different uplift zones here by color. So we have low uplift zone, high uplift zone, and transition zone. The top panel here is the normalized channel steepness for each basin. What we can see is that in the high uplift zone, the channel network is steeper. So we have high KSN values in this region. And the channel steepness is lower, both in the low uplift zone to the south and the transition zone to the north. In contrast, if we look at the drainage density for each of these basins, so that's shown in the middle panel here, we see that the density of the channel networks in each basin tends to be relatively invariant with uplift rate. And this makes some intuitive sense if we think that what we're measuring here is a measure of vertical motion, which is perhaps less likely to affect the kind of plan view organization of the drainage network. So that's the river profiles, but we then want to go beyond this to look at how the hill slope and hilltop morphology compares to the uplift gradient. And this can allow us to extract some extra information about uplift, which I'll come to in a few slides. So we mapped every hilltop across the study region, which is shown here in red. And then we routed flow from each of these hilltop pixels down to the nearest channel. So those flow paths are shown by these black lines, and the channels are shown here in blue. And then, as I said before, this allows us to get a number of different other topographic metrics, including hilltop curvature, or the steepness of the ridges, hill slope lengths, and the hill slope relief, so the elevation difference between the hilltop and the channel. So let's take a look at the results of how the hill slope and hilltop metrics vary with uplift. So this plot here, I'm showing you hill slope length across the uplift gradient. And we find that similar to drainage density, hill slope length is relatively constant with uplift rate. And this actually correlates well with kind of theoretical conceptualizations of the links between hill slope length and drainage density. So they should be inversely related to each other. It's a different story with hill slope relief, however. So here I'm plotting normalized hill slope relief in this graph. So this is following work by Roaring et al. In 2007, where we can define a dimensionless hill slope relief by normalizing it to the hill slope length and the critical slope. And if we plot this against uplift rate, we find that, again, we have the highest hill slope reliefs in the highest uplift zone. And in fact, if we look at the distribution of hill slope relief in each basin, so the kind of gray bars here are the 16th and 84th percentiles of the distribution. We tend to find quite a narrow distribution of hill slope reliefs within the basins. We also find that basins in the south, which are now in the low uplift zone, show elevated hill slope relief compared to basins in the north, even though the uplift rates here are lower. And we suggest that this difference is due to the lag time between channel response and hill slope response. So hill slopes will be slower to respond to a change in uplift compared to channels. We can then look at hilltop curvature, and we might think of hilltops as being the kind of last area of the landscape that will respond to a change in uplift. And this top graph here is the steepness of the ridges in each of the basins. And although we do find the highest hilltop curvatures in the highest uplift zone, I'd like to draw your attention here to the basins at the north end of this high uplift zone, so say basins 5 to 7 here. These still have low curvature despite the fact that the uplift rate is very high here. And this again is probably due to the fact that the curvature will lag behind the other metrics in its response to uplift. But the fact that these hill slope metrics show a different relationship to channel steepness with these different lag times actually allows us to track the northwards migration of the uplift wave from topography alone. So in order to demonstrate that further, I'm going to show you some plots here where on the y-axis we have hill slope relief, and on the x-axis we have channel steepness. So to make that more simple, I can just change these axis labels here. So we've got steepness of hill slopes on the y-axis, steepness of channels on the x-axis. And here we're plotting each of the basins, and they're colored by their location. So northern basins are colored in blue, dark blue, and southern basins are colored in yellow. And we can then compare each of these basins to our uplift gradient and the location of these 3 uplift zones. We can have a look, here I've marked the migration of the triple junction through time, so it's going from south to north. So when we're in the transition zone to the north, so that would be these dark blue basins here, these basins are only just experiencing an increase in uplift rates. If we look at their position in this hill slope steepness, channel steepness space, we can see that they have relatively low hill slope steepness compared to channel steepness. And this is because the hill slopes are taking longer to respond to the increase in uplift rates compared to the channels. The basins in the high uplift zone, in comparison, plot up here in this space. So they have both steep hill slopes and steep channels. So we could say here that these basins are fully adjusted to the uplift rate conditions through the Holocene that we can date from these terraces. The basins in the low uplift zone to the south, on the other hand, they would be these yellow basins here, have higher hill slope steepness compared to their channel steepness. This is because the uplift rate here is lower and therefore, or has lowered through time. And we can therefore think of the topography here as relaxing as the uplift rate is decreasing. The channels again respond to this relaxation faster than the hill slopes, and therefore their channel steepness is lower. So this means that we can use these basins as a kind of space for time substitution. So if you can imagine that you're a basin, you would start off in the north. So you'd start down here on this plot, and you'd follow a path through hill slope channel steepness space, going something like this as the uplift wave moves north through time. And this is really important because it means that just through topographic data and by combining the analysis of hill slope metrics with channels, it means that we can detect not only spatial, but also temporal changes in uplift. So I just want to wrap up my talk there and just briefly give some conclusions and kind of new opportunities that we could learn from this. So I've shown that we can detect tectonic signatures from topography on a range of different spatial scales. So we can do broad scale analysis of entire fault systems on a continental scale, or we can look in more detail at uplift signals over the scale of individual basins. And both of these things, I think, give us useful information about the interactions between topography and fault dynamics. Topographic analysis now allows us to explore changes in uplift rates in time. So from the first part of my talk, I showed how we can compare long-term topography and river profile gradients to modern earthquake data or horizontal slip velocities from GPS and INSAR. And this might give us insight into the kind of time scale of different fault behaviors. And finally, if we go kind of beyond river profiles and we link channel morphology to hill slope morphology, we can track changing uplift rates through time from topographic data alone. So thank you, I'll stop there and take any questions.
Great, thank you so much, Fiona, for a fantastic talk. At this point, I will turn it over to Steffi and Pierre, who will be taking, oh, I see we've got an outpouring of questions coming in. So they'll be kind of repeating those while we leave the slides up so we can discuss further.
Yeah, great. Let me just try and work out how to scroll up on the chat.
Hopefully they will be able to just kind of read the, yeah, either way.
Yeah, hi, Fiona. I might just start. Thanks a lot for the really nice and clear talk. I would just start by looking at the questions in the chat. And the first question that comes up was, did the study area had a transpressional orogeny? I actually don't know when this was asked. So if it was related to your first or your second case study.
Yeah, so the system is generally strike slip, but there are definitely areas of compression that we saw, such as at the Big Bend, where you have the restraining bend of the fault, and we therefore have uplift. So I don't know if that answers the question. I'm not quite sure what it means.
Yes, so maybe the person who asked the question could just like repeat it with more detail in the chat, or the other option is also to raise your hand and we can unmute your microphone if you want. So questions can be clarified if necessary. Or in general, if anybody wants to ask a question just by turning on the microphone and not using the chat, that's also totally fine. Just raise your hand and we will unmute you. Okay, Pierre, do you want to continue?
I'm taking the second question. Hi, Fiona. So the second question is from Sarah Titus, who really enjoyed the talk. And she's thinking that creeping segment has been longer lived, maybe for several million years based on patterns of off-fault deformation. So thinking along these lines, she's wondering if you see any offset between your peaks on the North American and PAC plates side of the fault on either end of the creeping segment. Because if so, maybe you could use that displacement to estimate how long this segment of the fault has been creeping.
Yeah, that's a really good question. I haven't actually looked at that in a lot of detail, but that would definitely be possible to do. So I can actually, maybe I'll just go back to that slide and take a look again. Just have to go back a bit. Yeah, so here, we definitely see some offset between them, but I think on the northern end of the creeping segment, the peaks look to be quite consistent. But this would definitely be something that we could explore in more detail. I think you could definitely use that to try and estimate how long it had been creeping for if we could assume a kind of constant slip rate through time and then measure the displacement. Yeah, that would be a really great thing that I can look at. Thank you.
Okay, so Ayush Yoshi was the one who asked the first question, and I think he would like to be unmuted. So I'm going to ask him so he could specify his question he was asking in the beginning. So you have to unmute your microphone if you would like to ask your question. Okay, so apparently that doesn't work, or he's not unmuting the microphone. So in that case, I'm just continuing with questions from the chat. There's so many questions, I have to scroll up again. So the next question in line would be from Will Strubble. Yeah. He also thanks you for the talk. I said it was a great talk. I'm curious about the role of landslides or earth flows along the Mendocino triple junction. Both how they affect channel steepness, as well as your measurements on curvature at the hilltops.
Yeah, thanks, Will. That's a really good question. So we didn't actually, in this paper, map landslides or earth flows from the data. I know that Georgie Bennett has done that in previous work, looking at the distribution of earth flows. I think they'll definitely affect the results, and they're probably a reason why we see this constant hill slope length across the basins. If we reach a point where the hill slope lengths are controlled by landsliding, I think that's likely to be an important control. They will affect the hilltop curvature if there is bedrock exposed at the hilltops, because our calculation of hilltop curvature assumes a soil mantled landscape. But I think as long as they don't initiate right on the ridges, then it shouldn't influence the calculation of hilltop curvature too much.
Yeah, I'm taking the next question. There's a comment from Rachel Bosch, who's saying fascinating talk. Thank you, Fiona. And then there's a next question from Aaron Buch, who is saying, hi, Fiona, thanks for the great talk. About the different timescales between channel and slope adjustments, have you tried quantifying the adjustment timescales? from known migration rates of the triple junction. Maybe this could be compared with models or used to calibrate these models.
Yeah, thanks, Aaron. That's a good question. We haven't compared it with models, but we did some back of the envelope type of calculations where we assumed that the triple junction was migrating northwards at around 5 centimeters a year. And I think that we got adjustment timescales of the hill slopes of being kind of greater than 1 million years in order to see the results. And I think channels were less than that. That's all we could do from that back of the envelope calculation. But I think there's a lot more you could do here if you combined this with a landscape evolution model and then had that migrating uplift wave as part of this scenario, then you could maybe constrain that in better detail.
Okay, thanks. So there's another person raising the hand. I'm trying again to ask the person to unmute. So Arindam, you should see a window popping up. Yeah, that worked. Okay, the next question by you, please.
Hi, can you hear me?
Yes.
Yes.
Hello. Hello.
Yes.
Can you hear me, guys?
Yes, we can hear you.
Yeah. This is Ari from Northeastern Hill University, Shillong, India, and great talk, Fiona. And I have just a query. Like, is there any relationship between the tectonic fault and faults change in the phase of the climate change?
I'm not sure I heard the last part of the question properly. Did someone catch it?
Yeah. I'm just asking that, is there any relationship between the tectonic structure and instability along with the phases of climate change?
With climate change? Yeah, that's something that we haven't looked at in detail. I think it would be quite difficult to compare it to past climate change. I'm not sure what data sets we would need for that. In terms of modern climate, we know that there's a big gradient in precipitation and vegetation along the strike of the fault. So this was originally something we thought might be a big control on channel steepness, but it doesn't seem to be. Like, we don't see a specific pattern of having steeper channels in the north compared to the south, for example. I don't think I answered your question very well, but well.
Thank you very much.
Thank you.
Okay, I will take the next question, which is from Benjamin Crosby. In the MTG case, how do the results changes if you plot basin characteristics versus distance along the fault rather than by basin number?
Yeah, I can maybe go to the map of the basins, which would kind of show that. So these are the basins that we analyzed here. And you can see that while there is some variation in the spacing between the different basins, this doesn't really affect the trend of the results. I don't have a plot of that to show you, but the uplift rates that are calculated are associated to each of those individual basins. So whether you plot distance or basin number shouldn't change the relationship with the uplift rate and the basins.
Okay, then we continue with the next question. That's from Victoria Milanes Fernandez. Thanks for the talk, Fiona. I noticed that in your second case study, there was a large range in the KSN values for the catchments. I wonder how noisy were your slope area plots and whether that was taken into account in generating your measurements.
Yeah, good question, Victoria. So we actually didn't use slope area plots when calculating KSN here. We used integral profile analysis, but there is definitely a big range in the channel steepness values in the catchments, especially within the bigger ones. So we think this is probably due to transient adjustments within the catchments to the uplift rate signal. So it might suggest that not all of the basins are fully adjusted to the modern uplift rates that we can measure. And this is probably especially true in the basins to the far north in the transition zone. But yeah, that's a good point.
I'm taking the next question from Eitan Shelef, who is thanking you for the fascinating talk. Regarding the MTG study, given that both drainage density and yield relief are influenced by the location of the channel head, he is wondering how was this point defined, and if it is defined the same everywhere along the study area, based on some threshold drainage area or alike. And similarly, was the critical slope SC defined as a constant along the study area?
Yeah, thanks. That's another good question. So the location of the channel head will definitely influence the drainage density and the hill slope relief and the hill slope length that we calculate. So to do this, we used a curvature-based method. So there have been a number of studies that have shown that the curvature-based method of calculating channels, so we look for a threshold of positive planform curvature to define the channel network. And several studies have shown that this can predict channel heads accurately within tens of meters. So I don't think that will influence the results too much. The threshold is constant through the study area, so that would be the same for each of the basins. Also, the critical slope, we did define that as constant through the study area as well, yeah.
Okay, so then I'll take the next one. It's by Kai Deng. And he first of all thanks you for the fascinating talk. And he actually has two questions, so I'm going through them just one by one. The first question was related to the first case study. A large portion of the hard igneous rock outcrops in the Big Bend where slope peak also exists. Sounds like lithology could play a role there.
Yeah, so I think lithology definitely plays a role on a kind of smaller scale in determining the channel gradients. And within the individual 1 kilometer bins, we have a lot of variation in channel gradient within each of those bins. And I think a lot of that's definitely lithology based. But I think when we looked at it over the broad scale of the entire fault system, it didn't seem as if lithology was the dominant control on where the peaks in the channel slopes were.
Okay, and then the second question is related to the second case study. From the low to highest uplift zone, uplift rate zones, uplift may increase by 1 order of magnitude, but the KSN only increases by 2 folds. So therefore there's a large discrepancy. Do measured uplift rates and steepness values represent processes integrating over different timescales here?
Yeah, this is a good point. It definitely seems like, yeah, there is a high increase in KSN in the catchments in the high uplift rate. This could be a result of discrepancies in the measured uplift rates from the terraces, or it could be the influence of transient processes within the basins. So if we have big nick points or things like this, we could be over steepening the channels at these places. I'm not particularly sure why there is a big discrepancy between them, but that's something, it's definitely a good question that we could go and look at in more detail.
Okay, I think so. We have the written question from Harry, who was asking them the relationship between tectonic structures, slope instability, and climate change. So I don't know if it's clearer for you when it's written, Fiona, or if you want to elaborate more on this.
No, I think I answered that in the question, so I don't really have anything else to add on that.
The second question is from Nilesh Zeshwara, sorry if I didn't pronounce it well, who is asking how will drainage reorganization impact the steepness of hill slope versus channel analysis? And thanks for the fascinating talk.
Yeah, that's a really good question. I'm sure that drainage reorganization will have a big impact, and it actually makes a big difference which basins you choose. So we actually did the same analysis on the basins on the other side of the ridge. So if I can use a laser pointer here, can you see that okay? We extracted all the basins on the other side of the ridge from these ones, and we performed the same analysis. And we found if we did that, that the hill slope metrics didn't seem to have the same relationship with uplift as on the coast, as the coastal drainages. And we suggested that this might be a result of drainage reorganization, which could definitely influence the relationship between uplift and hill slope metrics. So yeah, really good point.
Okay, so I would have a question myself at this point.
Yeah.
It's regarding the first study, when you were looking at the channel gradients, and you had these 4 peaks basically going along the coast,
Yeah.
and the first peaks you were looking at, you referred to the transition from the locked part and the creeping part.
Yeah.
And I was just wondering if you could maybe explain a little bit this mechanism that causes uplift in these transition zones. Because I mean, at least what I think about is that it definitely influences the base level or the outlet, but how does it actually cause uplift of the entire basins in that region?
Yeah, that's a good point. I think it's because you get a lot of strain building up in the crust where it's locked, and then when it becomes freely slipping. So there's been a lot of modeling work done that's shown that if you have that transition, you get very focused uplift and subsidence at the 2 transition points. But then you also get a kind of quadrant pattern of uplift and subsidence over long, like through the plate. So I think it's a result of strain buildup in earthquake cycles is what causes the uplift there. But it's quite localized. It's really like quite close to the transition points from modeling data anyway.
Okay, thanks a lot. And actually, while you answer that question, another one came in, again from Will Strubble. It looks like the slip rate along the San Andreas you were measuring was mostly from measurements over shorter timescales like GPS or INSA. Have you considered uplift and slip rates averaged over several seismic cycles?
Yeah, thanks, Will. That's a good question. Yeah, we've thought about this. So I've just downloaded some geologic slip rate data, which I'm going to try plotting soon. We've also looked at the thermochronometry along the San Andreas Fault, but I ran into a bit of a problem in that being too long time scale, in that because the fault is obviously moving laterally, it was difficult to relate a thermochronometry sample at one point to the channels at the channel geometry at the same point. So I think it's doing it over long time scales is actually hard as well, because you have to think about the plate migration too. So it's actually really difficult to find slip rate or uplift rate measurements that are appropriate to that of channel response times. So that's been a big challenge that we've had to deal with.
Great. Well, if you have another question, you have about 30 seconds to type. But otherwise, we'll thank Fiona again for the really exciting talk. And thank you all for coming, and remind everyone that the last talk in our series will be next Thursday at this same time. Thank you all very much.
Thank you.
Fiona, if you're still there, we have a last minute hastily typed question that is, what about the horizontal stress field? Probably in the San Andreas case, I suppose.
Yeah, so we've looked at the horizontal motion from the INSAR data. We've not looked at the stress field as of yet. That's potentially something I could try and look at. I'm kind of drowning in data sets at this moment, so try and see what I can get from the horizontal motion, but I think that would definitely be a good thing to consider too.
Great, thanks very much. All right, we'll sign off now. Thanks, everybody.
Great, thank you.